Hi everyone, this is section 4.2, combining and composing functions. In this section, we're going to learn some basic operations of functions. We're going to form composite functions. We're going to find the domain of a composite function, and then we're going to combine and compose in some of our application problems. First, we're going to talk about just some terminology as far as combining functions goes. Combining functions is a fancy way of saying we're going to take two functions and add, find the sum, subtract, find the difference, multiply, find the product, or quotient, divide them. And we've been doing this a little bit with some of our other functions before. You're going to see some cost, revenue, and profit functions later on in the lesson that will look familiar. The notation that goes along with these can be written a couple different ways. For example, if I wanted to sum two functions together, function f and g, I could write it like this, or we could write it like this. I personally prefer this notation, so I'll be taking the condensed form and splitting it into two separate functions added together or subtracted or multiplied or divided when I do them, but you can absolutely keep it in this notation as well. So it's going to look the same for difference, multiplying, finding our product, and quotient, finding dividing them. There is a little note with our quotient that our denominator cannot equal 0, and we know that that's a fact because of our domain restrictions that we've talked about in the past before. So that will come up in some of our problems, and then also in MyMathLab you may be asked to find the domain if you divide the two functions, and we're going to be focusing in on the denominator for those. All right, so in our first few problems, we're going to evaluate functions that have been combined. Here I have function f and function g, and then I have some notation that's asking me to do a calculation. It's written f plus g of 5, and I mentioned before I like the notation where it's separated into two completely separate functions. If I separated it, it would look like this, f of 5 plus g of 5. So notice 5 is being evaluated into each of these functions, and then we're adding them together. So you're going to evaluate first and then perform the operation second. So you can kind of do this off to the side. If I plug 5 into f, 3 times 5 minus 1, that would give me 14. If I plug 5 into g, that would be 5 squared plus 2, which gives me 27. And then 14 and 27, if I add those together, I get 41. So that would be the final answer here. Let's try the next one. I have f minus g of 7. Again, I'm going to rewrite that as f of 7 minus g of 7. And we're going to plug 7 into both functions. So 3 times 7 minus 1, that would be 21 minus 1, and it would give me 20. If I plugged 7 into g, it would be 7 squared plus 2, which would be 49 plus 2, or 51. And then if I subtract 20 minus 51, I get negative 31. F times g of negative 2, I'm going to rewrite it as f of negative 2 times g of negative 2. And again, plugging negative 2 into both of my functions. 3 times negative 2 minus 1, that's a negative 6 minus 1, so a negative 7. If I do negative 2 squared plus 2, I get 4 plus 2, which is 6. And if I multiply those together, my final answer will be negative 42. Finally, f divided by g of 0 would look like f of 0 over g of 0. F of 0, that's 3 times 0 minus 1. That just gives me negative 1. G of 0 would be 0 squared plus 2, which would give me 2. And negative 1 divided by 2 is just negative 1/2. That doesn't reduce, so I can leave that as my final answer. Okay, same type of problem here. Instead of an equation, though, we have a graph that we're going to find this information from. So you can see here in kind of navy blue, I have a graph of function f of x, and in purple, I have a graph of g of x. And here we want to find f plus g of negative 1. So f of negative 1 plus g of negative 1. So f of negative 1 means x is my negative 1. and I want to find the y that goes with it on this graph. So I'm going to find -1 on my x-axis, and then I'm going to go either up or down to function f. In this case, I would have to go up to get to function f, and think of this like finding the missing half of the coordinate. The point -1, 2 is on function f, so f of -1 evaluates to 2. If I want to find g of -1, I would also start at -1, but this time I would go to function g, which function g, that purple line, is at +1. Add them together, I get 3. So let's look at another one, f times g of 3. So that means f of 3 we need to evaluate, g of 3 we need to evaluate, and then we're going to multiply them together. So here's 3 on my x-axis. If I go all the way down to function f, that's at -4. If I go down to function g, that's at -1. And if I multiply those together, I get a +4. Finally, f divided by g of 2, that's f of 2 over g of 2. Finding 2 on my x-axis, that's here. To go down to function f, I'm at -2. And you can see that function g is actually on the x-axis at 2. So that means the missing half of my coordinate is a 0. Now, if I had 0 divided by -2, if this was flipped, my answer would be 0. But because we have a 0 in the denominator, remember that gives us mathematical error. So we're just going to say no solution or undefined. Okay, here are a couple evaluating and combining problems for you to try. In parts A and B, you're going to use the equations, and in part C, you're going to use the graph to the right. Okay, so in the first one, I'm going to find f of 2 plus g of 2. And to find f of 2, I'm going to do that off to the side here. That would be -5 times 2 plus 3. That should have been -7. G of 2 is -2 times 2 squared plus 1. And you can always use your calculator to help you with these if you need to. 2 squared gives me 4 times -2 is -8 plus 1 is also -7. If I add those together, I get -14. Should have been your final answer for that one. For the one below it, I'm finding g of 7 times f of 7. So plugging 7 into both functions, if I plug 7 into g, it's -2 times 7 squared plus 1. So 7 squared is 49 times -2 is -98 plus 1 is -97. F of 7 is -5 times 7 plus 3. That's -35 plus 3, which gives me a -32. And then we need to multiply those together, which you might have needed a calculator for that one because they get a little big. It's 3,104. Finally, the problem on the bottom, f of -2 divided by g of -2. F of -2, we're going to find -2 on the x-axis, and actually function f is right there, so that's a 0. G of -2, we would have to go up to our function, that's at 2. 0 divided by anything gives me 0. Okay, so now let's look at some problems where we're actually combining functions together to get a new function. So we're going to find 4 different things here, the sum, the difference, the product, and the quotient, and then we're also going to find the domain of the quotient at the end. So again, f plus g of x means f of x plus g of x. We're just adding the functions together. So that would be function 2x plus 1 plus -3x minus 5. And then as far as adding goes, all we're doing is combining together like terms. 2x and -3x give me a -x or a -1x. 1 and negative 5 give me a negative 4. And then that is your answer. We're creating a new function here, so we're not solving, we're not plugging numbers in. The new function is your solution. Next, we're going to find f minus g of x. So that's function f of x minus function g of x. Function f of x is 2x plus 1. If you are subtracting, you're going to need to make sure that you put whatever you're subtracting in parentheses, because this negative is something we're going to have to distribute in. So I'm going to put function g of x in parentheses, distribute my negative, 2x plus 1 plus 3x plus 5 when I distribute my negative, and then we add together like terms. 2x and 3x give me 5x, 1 and 5 give me positive 6. And again, that new function is our answer. F times g of x. So function f of x times function g of x. Function f of x is 2x plus 1. G of x is negative 3x minus 5. Notice I'm putting those both in parentheses because I'm multiplying everything in one function by everything in the other. And because I have 2 terms times 2 terms here, this is a FOILing problem. So review to do that. First terms, 2x and negative 3x are negative 6x squared. Outside terms, 2x and negative 5 are negative 10x. Inside terms will give me a negative 3x, and my last terms will give me a negative 5. Adding together my like terms, my final answer is negative 6x squared minus 13x minus 5. Okay, my final equation, we're doing f divided by g, function f of x, over function g of x. 2x plus 1 over negative 3x minus 5. And there are no factors, nothing I can factor out of the numerator and denominator, so there is no way to simplify this function. Only factoring the numerator and denominator would be a way to simplify. So this is our answer. Now if we want to find the domain of that, remember we can't have a 0 in the denominator. So we're going to take negative 3x minus 5, say that can't equal 0, and we're going to solve for x. So I'm going to add 5 and divide by negative 3. So this is telling me x cannot equal negative 5/3. So one way to say this is you could say the domain is all real numbers except negative 5/3, or you could put that in interval notation. That would look like negative infinity to negative 5/3, both with parentheses, and then negative 5/3 to positive infinity. Everything except negative 5/3. Okay, let's try another one. Same sort of problem here. First, I'm going to do function f plus function g. So function f, x squared minus 4, plus function g, 3x minus 6. Adding together my like terms, I have x squared plus 3x minus 10, and that's our final answer. F minus g, function f, minus, and make sure you put a parentheses around what you're subtracting, function g. We're going to distribute our negative, negative 3x plus 6, and then combine like terms, x squared minus 3x plus 2. F times g, x squared minus 4 times 3x plus 6. Again, notice I put those both in parentheses because we're multiplying everything in one function by everything in the other, so we're FOILing. First terms, 3x to the third here. My outside terms will be negative 6x squared. My inside terms are a negative 12x, and my last terms are a positive 24. Adding together like terms, we have a 3x to the third, a negative 6x squared, a negative 12x, and a 24. No like terms, so that's our final answer. Finally, we have f divided by g, function f divided by function g. Now this does factor a little bit. Let's see if we can reduce it. The numerator is difference of squares, so it factors into conjugates, 1 plus 1 minus. X times x gives me x squared. 2 times 2 gives me 4. The denominator, I could take a 3 out of both terms, and that leaves me with an x minus 2, just factoring out that common monomial. And then notice here that the x minus 2 is a common factor, so it cancels. X plus 2 over 3 is going to be our final reduced answer. Now, as far as finding the domain goes, there's no variable in the denominator in our final answer, but there is a variable in the denominator in the work. So even though my answer reduced, we're still going to set that 3x minus 6, technically not equal to 0 here, and figure out what the domain restriction is. So add 6, divide by 3, x cannot equal 2. So my domain is negative infinity to 2 and 2 to infinity. Or you might just be asked for the domain restriction, which would be 2. Okay, here is one for you to try. And you don't have all of them on here. You're just going to do subtraction and division, and then you're going to find the domain of your quotient. Okay, so subtracting function f minus function g. Make sure you put parentheses there. Distribute your negative x minus 2, and then combine together like terms. So final answer here should have been x squared, 1x or just x, minus 17. F divided by g, function f, on top, function g on the bottom. My numerator does factor here because I have 3 terms and there's nothing in front of my x squared. I'm looking for 2 numbers that multiply to negative 15 and add to 2. Those numbers are positive 5 and negative 3. And my denominator, remember, is x plus 2. So there are no common factors here, so nothing cancels in this equation. So you can just leave your answer like this if you want. Domain, denominator, cannot equal 0. So x cannot equal negative 2, which means my domain is negative infinity to negative 2, negative 2 to infinity. Okay, in our next group of problems, we're going to look at composing functions. Composing is a fancy way of saying we're going to be plugging one function into another function. And there are 2 ways that you're going to see this notation written. Again, I'm going to prefer the one on the right. If we see this notation, that means f composed with g, or if we see this notation with an open circle, it means f composed with g. This is very easy to get confused with multiplication. If it's multiplication, it's going to be a closed dot, and typically a lot smaller. If it's composing, it's going to be an open dot. So now what does this mean? If I see this notation, it means we are plugging function g into function f, and we'll see what that looks like, but it's going to look like a substitution problem, kind of like what we did with systems of equations. If I see a number there instead of an x, it means we're going to work from the inside out. It means we're going to plug 3 into the function that's closest to it, g, and then plug the answer we get into function f. So you, again, are evaluating 2 things, but you're kind of working inside one function, taking that answer and pushing it into another function. So make sure you have both of these notations at least written down in your notes. And then we'll do some practice problems first with evaluating, like we did with the combining problems, to see what these look like. Okay. So let's start with f of g of 2. I'm going to write it like this, f of g of 2, a double parentheses. And when you see a number here, we're evaluating from the inside out. So the first thing we're going to find is g of 2. So I'll do that to the side here. G of 2 is equal to 2 squared plus 4, which is 8. So that tells me that this whole piece on the inside can be replaced with 8 because that's what it's equal to. And now you can see what the next step is. We're going to take 8, the answer we got, and plug it into function f. So that would be 5 times 8 minus 6, 40 minus 6, or 34. So again, the procedure was we took 2 and plugged it into G, and then we took that answer and plugged it into F. So let's try another one. Here we're doing G of F of negative 5. So I'll write it like this, G of F of negative 5. Here the first step is to find F of negative 5. So again, I'll do that to the side. F of negative 5 equals 5 times negative 5 minus 6. That's negative 25 minus 6, which is negative 31. So I'm going to replace what's on the inside with negative 31, and I'm going to plug that answer into G. Negative 31 squared plus 4. 31 squared, you can just do that part in your calculator because again they start to get a little big. Plus 4, that's 961, plus 4 gives me 965. G of negative 1. G of negative 1. I'm going to plug negative 1 into G. Negative 1 squared plus 4. And that gives me 5. And actually, I probably should have done that off to the side, but you get the idea. So now we're going to replace G of negative 1 with 5. And so now we're taking negative 1, plugging it into G, taking that answer, plugging it back into G again. So I'm going to do 5 squared plus 4, which gives me 25 plus 4, or 29 is my final answer. Let's look at one with a graph now. Again, just like we did with the combining problems. So this is the same graph we saw before, but now we're going to compose. Notice the open circle, that's the big difference here when we look at the notation. So here we're finding f of G of negative 1. Again, we're going to start from the inside. G of negative 1 means find negative 1 on my x-axis, and then we're going to go to function G, which I would have to go up to get to the purple graph here, and that evaluates to 1. So the inside of the parentheses simplifies to 1. Then to find f of 1, we're going to go over to 1 on our x-axis, and actually at that point I'm on function f, the blue one, so that tells me my answer is 0 because I'm on the x-axis. Okay, the next one is G of f of negative 3. So f of negative 3 is what we're going to do first. So negative 3 is here. To get to function f, the blue one, I'm going to have to go up to 3. And now we evaluate G of 3. So we find 3 on our x-axis. We go down. Negative 1 is the final answer. Okay, here are a couple for you to try. You're going to compose, and I've already written it with the double parentheses here for you. Actually, there shouldn't be x's there. There should be some numbers there. Let's put some numbers there. How about a 3 and a negative 2 will work. And then use the graphs at the bottom to find G of f of 3. Okay, I'll give you a minute. Okay, so I'm going to first find f of 3. I'll just do that off to the side. Negative 5 times 3 plus 3. That's negative 15 plus 3, which is negative 12. Then we're going to evaluate G of negative 12, which would look like a negative 2 times negative 12 squared plus 1. And this you can type in the calculator. 12 squared is going to give you 144 times negative 2, which is negative 288, plus 1. Final answer here should be negative 287. Finding f of G of negative 2. So this time we're going to plug negative 2 into G first. So negative 2 times negative 2 squared plus 1. That's 4 times negative 2 is negative 8, plus 1 is negative 7. So now we need to evaluate f of negative 7. Negative 5 times negative 7 plus 3, which is 35 plus 3, which gives me 38 for my final answer. Okay, at the bottom, finding f of 3. So I'm finding 3 on my x-axis. Here I have to go down to get to function f, and that is negative 1. Now I want to evaluate g of negative 1. So I'm going to find negative 1 on my x-axis, go up or down to function g. In this case, I have to go up. Final answer is 3. Okay, so now let's try composing some functions. So anytime that you see this notation, or you may see a parentheses with an x around it, it just means we're plugging one function into the other, and just like combining, we're going to get a new function. So there's no number that we're plugging in, we're plugging a function into another function. All right, so starting with g of f of x, that means, I can write it like this, g of f of x, and I can say in words it means plug f into g. So what that's going to look like is we're going to take whatever function f is equal to, and we're going to plug it into function g wherever we see a variable. So we're going to take the variable out and replace it with 3x minus 1. That looks like 5 plus 4 times 3x minus 1. So this is very similar to what we did with substitution, as I mentioned in our systems of equations. And now we can simplify. In this case, I distribute 12x minus 4, and then I can combine my like terms. 12x, 5 minus 4 gives me positive 1, and that's my answer. F of g is the opposite. I'll do this one in a different color. I can write f of g of x, and I can say in words this means plug g into f. You can actually see in the notation g is inside of f. So we're going to do the opposite now. Function g we're going to circle. We're going to plug it into function f anywhere we see a variable. So that looks like 3. Take the x out and replace it with the other function, 5 plus 4x minus 1. We're going to distribute 15 plus 12x minus 1, and then combining together my like terms, my final answer is 12x plus 14. Now this problem also said to find the domain. When you're calculating domain of these functions, you want to look at the original functions first and see if they have any restrictions. And remember, restrictions come from a square root or a 0 in the denominator, or both. In both of the original functions, I have no square root and no denominator. If I look to my answers, I have no square root and no denominator. So we can quickly say that my domains are all real numbers. There are no restrictions. And we'll see problems in a little bit here that do have a restriction, so you'll be able to see what that looks like. Okay, let's try another one. We're going to first find g of f here. So I'm going to write g of f of x. And then I'm going to write in words what this means. We're going to plug f into g. So I'm going to circle all of function f, plugging it into function g anywhere I see a variable. So that will look like 2, take the x out, replace it, 2x squared plus 3x minus 1. Distribute 4x squared plus 6x minus 1, and then I have no like terms, so that's our final answer. Next, I'm going to find f of g, which I'm going to write as f of g of x. And in words, this is telling me to plug function g into function f. Again, anywhere I see a variable. So this one's going to get interesting. So we're going to plug 2x minus 1 into function f here and here, because there's two different variables in that equation. So I'm going to write down pretty much function f, but I'm going to take these x's out and put a 2x minus 1 in parentheses in its place. That looks like 2 parentheses 2x minus 1 squared plus 3 parentheses 2x minus 1. Now remember what it means for a binomial to be squared. it means that parentheses is multiplied by itself if I write this in expanded form. So we are FOILing here. F-O-I-L. First terms give me 4x squared. My outside terms are negative 2x. My inside terms are negative 2x. And my last terms, negative 1 and negative 1, positive 1. The 2 in front is still going to be distributed in, and then I'll bring everything else down as well. In our last two steps, we're going to distribute and combine like terms. If I distribute the 2 in, that gives me 8x squared minus 4x plus 2 plus 6x minus 3. And then combining together like terms, 8x squared. I have negative 4, and a positive 6, which gives me a negative 2x. And then finally 2 and negative 3, which gives me a negative 1. And that's our final answer, our new function created by plugging one into another. Domain again for both of these will be all real numbers. There are no restrictions in the original problems, no square roots or denominators, and no restrictions in our compositions as well. So domain is all real numbers. Okay, we're going to try one more together, and then you'll have an opportunity to practice these. Here we're going to find g of f first, so I'll write g of f of x. You can also write it in words. Plug f into g. So function f is going into function g, anywhere I see a variable. So that's going to look like the square root of 6x minus 2. And then there's nothing we can simplify there because of that subtraction. Can't reduce my radical, so that's our final answer. If I want to find f of g of x, that's telling me to plug g into f. So this time I'll use a different color here. Function g is getting plugged into function f, and that's going to look like 6, take the x out, put square root x in its place, minus 2. And again, nothing we can do to simplify there. We have no like terms, and my radical does not reduce. Now finding the domain. In this problem, we do have domain restrictions. F has no domain restrictions. Its domain is all real numbers, so that's good. But G does have domain restrictions. Remember, anything that's underneath a square root needs to be positive or 0. So X values need to be greater than or equal to 0. That's going to continue and carry through into our compositions as well. So for this function, we actually have the same restriction. You'll see my x's can only be greater than or equal to 0. So we say the domain is 0 with a bracket to infinity. Now the first one we did actually has a different square root in it. So we're going to have to solve here. 6x minus 2, remember whatever underneath the radical, we're going to say must be greater than or equal to 0. And then we're going to solve for x. So I'm going to add 2. And divide by 6, which 2 over 6 is going to reduce to 1/3. So here, my x's can only be numbers greater than or equal to 1/3. And earlier we said my x's can only be greater than or equal to 0. So this creates additional restrictions on what we started with. And it's almost like the intersection of the two. Only 1/3 to 0 or to infinity can be plugged in here. You can't plug in anything between 0 and 1/3. For example, like 0.1, if I plugged 0.1 in, 6 times 0.1 would give me 0.6 minus 2, which would be a negative number. So that would give me an error. So this ensures that whatever I plug into that function would not cause an error in the original functions and would not cause an error in my composition. And that's really what you're looking for when you're trying to figure out domain. So that's how you can check it. Pick a number in your domain that you've chosen and make sure in either of the original functions and in your composition you don't have any errors. Okay, here's one for you to practice. I am going to get you started a little bit because of the fractions, the form that these problems are taking. I'm going to rewrite function f of x as 2 separate terms. So I'm going to, this is the opposite of adding with a common denominator. It's separating with a common denominator. So I'm going to write it as 5x over 4 minus, if I do 8 over 4, I just get 2. So that's going to be a little prettier. You could also write 5/4 x minus 2, which because that x is now kind of separate from the fraction, it might make it easier when you're plugging something in. You can do the same thing for function g. I can make it 4/5 x plus 8/5, and I can't reduce that. Okay, try to find g of f and f of g. All right, let's see how you did on this one. So g of f of x, which if you wrote that in words, we're plugging f into g. So taking function f, putting it into function g where I see a variable. That looks like 4/5 times 5/4 x minus 2 plus 8/5. The first thing you should have done is distribute there and there. 4/5 times 5/4 actually just gives you 20/20, which is 1x. 4/5 times -2 is -8/5. Bring down my plus 8/5. Those actually cancel, and you are left with x. In the second one, f of g of x, which I can write like this, and if you wrote it in words, that's plugging g into f. So that looks like this. And we're going to plug that in there. So that looks like, I'm going to do this down where I have a little bit of space. 5/4, take my x out, put function g in its place, 4/5 x plus 8/5 minus 2. Distribute. Again, I'm going to have 20/20, which is just 1x, plus I'll have 40/20 if I multiply those fractions, minus 2. 40 divided by 20 is 2. Minus 2 cancels, and again you are left with x. Domain of both of these you should have said is all real numbers. We do have denominators in our original problem, but there are no variables in the denominator, so that means there are no restrictions. This is a little kind of precursor to the last lesson that we're going to see next week, which is about inverses. If you are able to compose two functions into one another like this, and you get x out both times, it's a proof that they are inverses of one another. Okay, let's look at some application problems now. Let's do this first one together. It says, suppose that the total weekly cost for the production and sales of TV sets is C of X equals 189X plus 5,460. So that's what it costs to make the TV. And then remember the revenue, which is the money that you bring in after the sales, is 988X, where X is the number of televisions, C of X and R of X are in dollars. Write an equation that models the weekly profit. So this is a little review from an earlier lesson. Profit is revenue minus cost. So this is actually a combining problem where we have two functions that we're going to subtract from one another. Function R of X is 988X, and function C of X, I'm going to put it in parentheses when I subtract, 189X plus 5,460. Distribute my negative, so I'm going to have 988x minus 189x minus 5,460, and that means my final profit function is, I'm going to have to combine those like terms there, 988 minus 189 gives me 799x minus 5,460. What's the profit from the sale of 8 TVs? You're just finding P of 80 here. So 799 times 80 minus 5,460 will calculate the profit. And by the way, you would get the same answer if you calculated the revenue with 80, the cost with 80, and then subtracted the two answers. 799 times 80 minus 5,460 gives me $58,460. These are some expensive TVs. Okay, write an equation that models the average profit. And average profit is something they're kind of throwing in at the end of this lesson. If you see a bar over a profit or revenue or cost, it's asking you for the average. Whenever you calculate the average of something, it's the amount for all of them together divided by how many you have. So if I want an average profit function, it's just taking my profit function, I'm going to put the little bar over it, that we found, divided by the number of TVs sold. Well, X represents the number of TVs. So divided by X is all we have to do, and we have a profit function for the average that we're going to make from each TV for the sales. Part D is just using that function now. What is the average profit per TV for the sale of 80 TV sets? So we're going to evaluate into this, and actually I could put an 80 in there if I want to. There we go. So that's going to be 799 times 80 minus 5,460 divided by 80. Now I know the numerator already. That was that 58,460 divided by 80. And I'm going to get 730.75 in 2 decimal places is reasonable here because it's dollars and cents. My profit per TV, if I sell 80 TVs, is $730.75. Our next application is ticket sales. At a certain school, the number of ticket sales sold for a football game can be modeling the following function if they're student tickets. So S of P represents student tickets, and it's 62P, so $62 per student ticket plus 8,500. Where P, it's not per student ticket, excuse me, where P is the winning percent of the home team. The number of non-student tickets, which is going to represent in an equation with N of P, is 0.5P squared plus 16P plus 4,400. And I'm going to underline there again, P is the winning percent of the home team. So here someone's found functions to model based on the percentage of the home team with their winning percentages. It's going to tell us how many student tickets and how many non-student tickets we can anticipate selling for the game. Write an equation for the total number of tickets sold as a function of the winning percentage. So total number of tickets would be student tickets plus non-student tickets. So that's the calculation we're doing. We're doing functions S plus N of P, and P is going to be the input ultimately. So we're just adding our equations together, which we know is just adding together any like terms. So here's my function, and it is equal to 0.5P squared. I have a 62P and a 16P. That gives me a 78P. And then I have 8,500 and 4,400, which give me, let's try that again, 8,500 plus 4,400. Got a weird number in my calculator. There we go. 12,900. What is the domain for this function in the context of the situation? So the domain of this function is going to be calculated by finding our possible P values. Okay, and P technically could be all real numbers here because I don't have any domain restrictions in the function, but remember what P stands for. P stands for a winning percentage of the home team, and because it's a percentage, we're really limited to the type of numbers that P can be. So percentages range from 0 to 100, so my domain is 0 to 100, and you can see I'm using brackets on both of those because you can have a winning percentage of 0 if you have all losses, and you can have a winning percentage of 100 if you have all wins. Assuming the stadium is filled to capacity when the team wins 90% of its games, what is the capacity of the stadium? All right, so we're going to evaluate into our function 90, and that's going to tell us how many tickets they're going to sell if the winning percentage is 90%, and therefore also tell us the capacity of the stadium. So 0.5 times 90 squared plus 78 times 90 plus 12,900. And this is something you can just type in the calculator. Just use parentheses, be careful with it. And I get 23,970 is the capacity. So we'll label it people that can fit in our stadium. Okay, the final problem here is yours to try. Again, this is a profit function, so this is similar to the one we did a couple slides ago. Part A, you're going to write the equation for the profit function. Part B, I want you to, it's just a little review, name if that function is linear, quadratic, or neither. And then C, find the profit from 49 golf carts. All right, so my profit function is, again, my revenue minus my cost. My revenue is 26,600x minus my cost, which was 200,000, plus 4,600x plus 2x squared. Distribute my negative. And then combine like terms. So your final function here, and I'm going to put my terms in order, exponents highest to lowest always, negative 2x squared. If I do 26,600 and subtract off the 4,600, I get 22,000 minus 200,000. Is it linear, quadratic, or neither? The answer is quadratic because you have an x squared as your highest power. And then finally, you're going to evaluate that function into, we're with 49 for the number of golf carts they're going to sell. Okay, so we should have plugged in 49, and then again, you can use your calculator to help you here. So 49 squared times negative 2. You can just really type it all in one line in your calculator if you don't want to get too crazy with the order of operations. Plus 22,000 times 49 minus 200,000. And I get a grand total of 873,198 is the total profit. If you wanted to find out what profit that is per golf cart, I know it didn't ask for that here, but you could divide it by 49 and you would get approximately $18,000 per golf cart. Again, some pretty fancy golf carts.